So good evening everyone. I guess we can start now. So for today's session what we'll have is we have covered how to reduce blocks and block diagram method and Mason's chain rule and the time response of first and second order linear systems. So I can see many familiar faces and can you guys tell me which part was the most interesting and which one was the most difficult this week? Yeah, and I'm audible, right?
Yes, audible. सर मुझे सिग्नल पर ग्राफ और ब्लॉक डिटेक्शन में तो कोई प्रॉब्लम नहीं होगा, बस टाइम डोमेन पैरामीटर में प्रॉब्लम होगा सर।
ओके ओके,
क्योंकि ग्राफिकल जो प्रॉब्लम होते हैं ना सर उसमें प्रॉब्लम।
अच्छा हाँ, okay, we'll look into I guess 1 or 2 questions similar to that. Hopefully that will clear your doubts. So I guess we can start now.
Yes.
So first question for today is find the transfer function of the given system. So when we have a block and we want to find the transfer function, basically we want to find the ratio of ys to us, right? Ys to us. And the issue when we have a complicated block or many input output channels is that we don't know exactly what is coming through which channel, right? So when we see this question, first we can see that when at this node, at this summation node, one input is the input to the system. Okay, so that part is clear. This signal is U of S. Now this one and this one will depend on what will happen at the output end of the signal, right? So like through this one Y of S is coming and through this one this point value is coming. Let's say it is X of S. Okay, so we can say this is X of S. Yeah, so what I was discussing is we have a block of this manner and just a minute, some students are joining in. Yeah, okay, I'll recap this question a bit. Given is a block diagram and I want to find out the transfer function y of s by u of s. Okay, so first for any general question of this kind, what we do is we start from a place where we know things. Like the input is something we know, so we'll start at this summation node. Then at that summation node, we see that there are 3 input channels. So one input channel is the input signal itself, so there is no issue with that. So here we have U of S plus this channel and this channel. The someone is unmuted. Yeah. So this bottom channel is Y of S. This point is connected back to the summer. So here we have Y of S. And this upper channel is coming from some point in the middle and let's say that is X of S. So here we have
minus Y of X and minus X of S.
Yes, sorry. Yeah, minus Y of S and minus X of S. So here we are getting into the input into the system is U of S minus X of S minus Y of S. So now here also we have this signal. Now that signal goes this way and this way, gets multiplied with some blocks, comes out and then that is added, right? So let's write that this signal into S on the upper branch and into 1 by S on the lower branch. then both of them are added. So we can write this is s plus 1 by s. And that is what? That is this point, which is nothing but x of s. Okay, we have one equation till now. Then for the next part, we can see that x of s multiplied by 1 by s is y of s. Correct? So no, like here no other input branches are there. So we need not worry. We can straight away write x of s into 1 by s is y of s. So now we have these two equations and one unknown, that is x of s, because we want to find the ratio between y of s and u of s. So we have to eliminate x of s from this equation. So from here we can write x of s is s into y of s. So then when we substitute this back into this equation, what we have is u of s minus y of s minus s into y of s whole into s plus 1 by s is equal to s into y of s. Now we can we can write this equation one side in terms of u, the other side in terms of y. So we have u of s into s plus 1 by s is equal to y of s into s plus s plus 1 by s plus s into s plus 1 by s. So this thing becomes so this thing becomes s plus 1 by s and on the left hand side we have which is this square bracket term is this thing, and on the left hand side we have s square plus 1 by s. So everything gives us y of s by u of s is nothing but s square plus 1 by s cube plus 2s square plus s plus 1. So this is the transfer function of the given system. Is this whatever we did for this question, is it clear? Are there any doubts?
No, sir.
Okay. So I'll just recap once again. We had the input channel, the other two, whatever we knew, we wrote it as what we knew, and the other things we assumed, and slowly we just kept pushing the input towards the output side. Then we'll get enough equations to eliminate the number of unknowns, and we can finally write the output in terms of the input. That will give us the transfer function of the system. So now we have a question of how to use the Mason's gain rule. So we want to find out the system gain y by r. Can someone help me with the formula for the Mason's gain rule?
Yes, sir. Summation of k is equal to 1 is equal to n pk del k by del.
Okay, so this is the formula of the rule. This is the formula for the gain of any given system. So where k is the number of forward paths. So let's first find out that. So how many forward paths can you count here?
2.
Okay, can you name them?
2 forward paths. 1, 3, 4, 5, 1 and 1, 6, 1. 1, 6, 1.
Yeah. So there are 2 forward paths. Now next is we need to find this tk. So for tk, as you know, as you guys told me, 1 into 3 into 4 into 5, this is for 1 into 1, that is 15, no, sorry, that is 60, and T2, which is just 6. Okay. So now tell me what delta should be. Before that,
tell me how T1 is calculated.
Okay, so Ti are basically the forward gain of the forward path. So we saw that this is one forward path and this is another forward path. So for the first forward path, we just calculate the gain 1 into 3 into 4 into 5 into 1, which is 60. Is that clear?
Okay, understood.
Yeah. So next is we want to find delta. For that we know delta is 1 minus sum of loop gains plus sum of 2 non-touching loop gains minus sum of 3 non-touching loop gains and so on. So for this, first tell me what are the loops.
4, sir. Number of loops equal to 4.
Number of loops equal to 4. Okay, tell me the gains. Which ones are the loops?
Individual loop are 3, sir.
So
3 loop gains.
First, sir, loop gain is 3 into minus 1, sir.
3
and
into minus 1.
4 into minus 1.
4 into minus
and
1.
5 into minus 1.
5 into minus 1
and 6 into minus 1 into minus 1 into minus 1.
Correct. So for the 4 loops, first one is minus 3, minus 4, minus 5, then 6 into 3 times minus 1 is just minus 6. Okay, so these are the 4 individual loops. Now tell me if there is a pair of non-touching loops.
Minus 3 and minus 5.
Into minus 1 and 5 into minus 1.
Okay, minus 3 into minus 5. These two are non-touching. Any other pair if we take from these 4, we'll see that they are touching. 2 non-touching loops. So the gain is minus 3 into minus 5, 15. And since we have only 2 non-touching loops, we cannot have 3 non-touching loops. So these parts will be 0. So now we'll have delta is equal to 1 minus 3 plus 4 plus 5 plus, this will be minus of minus, so plus this, then plus 15, right? So this is, we have delta is equal to 34. Now we want to find out delta 1 and delta 2. So for delta I, what we do is we remove the corresponding forward path and then see whatever loop remains, if like whatever we have, and do the delta calculations for the remaining things. So first for delta 1, if we remove this line, tell me which loops will remain.
Delta 1 is 1, sir.
Yeah, correct. So that means no loop remains. So we have delta 1 equal to 1. Now for delta 2, that is if I remove this thing, what loop remains?
1 minus of 4, sir.
4 into
1
minus 1.
plus 4.
Yeah, this loop only remains, right? So delta is 1 minus minus 4, which is 5. So now as per the gain rule, the gain is summation k equal to 1 to 2, since there are 2 forward paths, tk del k by del. So here we have t1 del 1 plus t2 del 2 by del, that is, what is t1? 60 into 1 plus 15, plus 6 into delta 5 by 34. So we have 90 by 34, that is 45 by 70. So this is the answer for the Mason's gain rule.
सर
Yeah.
जब हम लोग एक फॉरवर्ड पाथ लेके चलते हैं तो क्या हम लोग ब्रांच को अलग करते हैं या सर नोड को अलग करते हैं डेल 1 और डेल 2 निकालने के लिए? सर
हम नोड को ही अलग कर देते हैं. We remove the nodes. Yeah. Basically they are removed from the graph. We only take whatever nodes remain and the branches between them.
ओके.
Yeah. So is this clear how we use Mason's gain rule to find the system gain?
Yes, sir.
Okay. And for this question in particular, we had only numbers as the gain, but you can replace this by any transfer function or whatever, and you can find the gain in the similar manner. That will give us the transfer function of some system. So we'll move on to the next question. A unit step input is applied to a unity feedback system and it results in a steady state error of 0.05. So what is the type of the system? So what we have is, we have some system G of S. We are giving unity feedback.
Type of the system is 0, sir.
Yes, correct. We'll get to that. And we are giving unit step. So unit step input is U of S. So first of all, unity feedback system, we have G as the plant, like the system, open loop system. So the unity feedback closed loop system will be G by 1 plus G, right? Yes.
Because of the step input, sir, we can directly say that it is a type 0 system, sir.
Yeah, we can directly say that. I'm just going through the process to show everyone who might not be familiar. Like, I'll get the error. Yeah. So this is the closed loop system, transfer function y. So the basically y is equal to G by 1 plus G into U, and the error will be just 1 by 1 plus G into U. So I want to find out the steady state error, right? So E infinity will be limit s tends to 0, s into error 1 by 1 plus G into U of s. And for this system, since we are giving unit step, it will be 1 by s, this will be cancelled, and what we'll have is 1 by limit s goes to 0, G of s. Now what is given to us is the error, steady state error is 0.05, correct? So if the steady state error is 0.05, that means limit s tends to 0, G of s is some finite value. So when the system state, like limit s goes to 0, limit s goes to 0, G of s. G of s will be some transfer function, some numerator by some denominator, right? So if this thing is a finite non-zero value, then what we can say is there is no s on the numerator, open s, and there is no open s on the denominator as well. So this can be anything, s plus a, s plus b, and so on, but there is no pole or zero at the origin for this particular transfer function, because this is 1 by 0.05, which is 20. So limit s goes to 0 is G of s is 19. So from that we can say that this transfer function is a type 0 transfer function, right? 0. Now from this you can see what will be the steady state error for a type 1 transfer function. So a type 1 transfer function will be something of the kind s plus a something s into s plus b something. So in a type 1 transfer function we will have a pole at the origin. So for a type 1 transfer function you can see limit s goes to 0, G of s is infinity, correct? So since this is infinity, the error will be in the form of 1 by infinity, so that limit will be 0. So E infinity in that case is 0 for type 1. So from this what we can say is, if I want my system to track some constant input, then the system should have an integrator, that is a pole at the origin. So without an integrator, I can never reach, my steady state will never reach to the desired output, and I will always have some small amount of error. It might be very small, like 0.05, but that error will persist. But if I have an integrator, that error will die down. So is this clear how we derived the steady state error formula and stuff?
Yes. ये प्लीज एक बार फिर से बता देते तो टाइप 1 के लिए और टाइप 0
क्या क्या बता दो, सुना नहीं दिया।
जैसे ये डेरिवेशन तो सब समझ में आ गया सर, लेकिन वो कैसे टाइप पहचाना गया वो नहीं।
अच्छा, टाइप कैसे पहचाना गया ना। सो टाइप ऑफ द सिस्टम इज डिफाइंड बाय नंबर ऑफ पोल्स एट origin. So this part, like question क्या था, यही था ना कि how to define type of the system, और the question was something।
स्टेडी स्टेट एरर देने के बाद हम लोग कैसे उसका कौन सा टाइप का है वो।
हाँ, ओके। सो हमारे पास like we have the steady state error 0.05 and that gives me this relation. Is it clear till here?
Yes.
Okay. So that means limit s tends to 0 g of s is some finite non-zero value. Correct. So if I had g of s as say s plus 1 by s into s plus 2, this is a type 1 system. So if I had this system, then can I ever say limit s tends to 0 g of s is some constant which is not equal to 0, some finite value? Will that ever happen?
When system is type 0.
Yeah. So basically, if I have a pole at the origin, one pole, two pole, or any number of poles, then limit s goes to 0 g of s will always be infinity. So a finite non-zero value for limit s tends to 0 g of s can be obtained only when the system is of type 0. So from that we can say that the system is of type 0, because if anything else, either type 1, type 2, type 3, whatever, we'll get infinity as the value for limit s tends to 0 g of s, and in consequentially we'll get the error going to 0, right? So that is why we always need at least one integrator for the system to track a step response. Is that clear?
Yes.
Okay. Any other questions in this part? Okay, I'll move ahead. So now a unit step input is applied to a unity feedback system, and it
last one type 0 system na?
Last one type 0, yeah.
Okay.
Yeah. A unit step input applied to a unity feedback system results in a steady state error of 0.05. So what is the position error constant of the system? Okay, so this is from the previous part only. We have limit s tends to 0 g of s as the position error of the system. So this is 19 as we found out in the previous question for this. So since we are talking about position error constant, I will just define the velocity and acceleration error constants as well. Goes to 0 s into g of s, Ka is equal to limit s goes to 0 s square into g of s. So the origin behind these error constants is that only, like we give us either a step input, or so for the position error constant we give a step input and see what is the steady state error of the system. E is equal to 1 by 1 plus g u. So if u is equal to 1 by s, then E infinity is 1 by 1 plus kp, right? 1 by 1 plus g of 0. But if I gave a ramp input 1 by s square, then basically what I am telling the system to do is I want it to track a fixed velocity. So when it tracks a constant velocity, its position will track a ramp. Okay, so that is the idea, like a notion behind the nomenclature of these error constants. So if I give a ramp input, then error will be 1 by limit s goes to 0 s into g of s. So this is just 1 by kv. And similarly, if I give a parabola, that is, I am telling the system to track a constant acceleration, so that it will track a fixed parabolic position value. So E infinity is 1 by limit s goes to 0 s square g of s, right? And for there to be zero steady state error, to track a ramp, I need to have a type 2 system, right? And for me to be able to track a parabola, I need to have a type 3 system, similar to how we needed a type 1 system to track a step input. So that is the idea behind all these error constants. Is this part clear? Any doubts in error constant or so how to?
सर
हाँ.
पाराबोलिक को ट्रैक करने के लिए टाइप 2 सिस्टम होना चाहिए ना?
पैराबोला को ट्रैक करने के लिए, so I want to track this thing. So basically this error has to be 0. So limit s goes to 0 s square g of s has to be infinity, right? So if I have a type 2 system, then I will have limit s tends to 0 s square into some s plus a by s square into s plus b into whatever. So this will be a finite value, correct? This won't be equal to 0 or infinity, but we want it equal to 0. So we need another pole at the origin, so that if I have limit s goes to 0 s square into something something by s cube into something something, then this will be infinity. So then the error, steady state error will go to 0, correct?
Yes.
Yeah. So okay.
तो ऐसा कोई शॉर्टकट ट्रिक जो याद करें, क्योंकि ऐसा प्रॉब्लम जो है ये सी और गेट में पूछते रहता है कि कब ये जीरो होगा, कब
हाँ, तो उसके लिए बेसिकली क्या बोलते हैं, टाइप 0. So if I have a type 0, then I will have steady state error for a step input, right? क्या जानना है exactly?
एक टेबल बनता है ना सर कि टाइप 0 में कौन सा 1 होगा, 0 होगा, इंफिनिटी होगा.
Okay. So okay. तो टाइप 0 होगा तो केपी फाइनाइट होगा, और क्या बोलते हैं जो नेक्स्ट वाला एरर, राइट? ई इंफिनिटी, मैं जस्ट लिख रहा हूँ, ये एरर कॉलम है. फॉर स्टेप होगा फाइनाइट एंड रैम्प कॉमा क्या होगा पैराबोला के लिए इन्फिनाइट एरर. ये ऐसा ही टेबल चाहिए ना?
यस.
ओके. सो टाइप 1 अगर है तो वी विल हैव kp इक्वल टू 0, kv इक्वल टू फाइनाइट, ka इक्वल टू इन्फिनिटी. Sorry, that will also be finite only. And step 0 error, रैम्प के लिए फाइनाइट एरर एंड पैराबोला के लिए इन्फिनाइट एरर. kp, kv equal to 0, ka equal to finite, and सिमिलरली स्टेप और रैंप के लिए 0 एरर, पैराबोला के लिए फाइनाइट एरर, और टाइप 3 होगा अगर KP, KV, KA सभी 0 होंगे और सभी के लिए एरर 0 होगा। करेक्ट? ये समझ में आ गया?
ये सही कोई ट्रिक्स है मतलब याद करने के लिए? जनवरी में भूल जाता हूँ सर, आगे पीछे हो जाता।
मतलब ऐसा ही लाइक बॉटम लेवल से चलना है, लाइक टाइप 0 लाइक स्टेप रैंप पर पैराबोला है, तो टाइप 0 में स्टेप में भी एरर आता है, बट टाइप 1 में स्टेप का एरर नहीं आएगा। तो ऐसा कर सकते हैं मे बी लाइक सो एक लेवल टाइप का बना लेंगे, स्टेप पैराबोला, और इसका होगा टाइप 0, टाइप 1, टाइप 2। करेक्ट? सो टाइप 0 सिस्टम कैन विल हैव, जो सेम लेवल में होंगे उनका फाइनाइट एरर रहेगा, बट हायर लेवल अगर स्टेप इनपुट आया तो उसमें 0 एरर होगा। ये ठीक होगा?
फिर से सही बात।
Like type 0 will have a finite error for step, infinite error for anything above the step. Type 1 will have a 0 error for step, so will anything below type 1, it will have 0 error. At same level it will have finite error, at upper level it will have infinite error. So type 2 के लिए बस इधर finite error, इधर 0 error, तो ऐसा याद रख सकते हो।
Yes sir, thank you.
Okay, let's move on to the next question. So the block diagram of a feedback system is shown in figure A. Find the transfer function CS by RS. So this is an easy question. I want you guys to solve this. Find the transfer function C of S by RFS.
G by S square plus 3S plus G.
G by S square plus 3S plus G. But I am getting response only from one student, 1, 2 or 3 students I guess. Yeah. Others also please be more interactive. Let's increase the discussion so that all of us can know. Okay. If you have any doubts, please do not hesitate to ask any questions. So yeah, this transfer function, I guess everyone is familiar with how to derive the transfer function for a unity feedback. I'll just do it quickly once. So if I have somewhere plus, this is minus, and something G, so this is Y, this is U, this is E, error. So E is basically U minus Y and Y is basically GE. So Y is G U minus Y. So Y is equal to GU minus GY. So Y into 1 plus G is equal to GU. This implies Y by U is equal to G by 1 plus G. Okay. So for any given system of unity feedback form, and if you have some H here, what you will get is G by 1 plus GH. So for any given system, you can directly write the transfer function in this manner. Okay, so I hope this is clear to everyone. We'll move on to the next question. So for the previous value, like this system, we want to find the value of G so that the closed loop response of the system is to a step input is as shown in the figure. So how do we do this?
We calculate
Maximum.
final value, sir.
Okay, wait.
Final value of our C of S.
Okay, that we can do. That is one thing. Kiran, you were saying something? Okay. So, see, final value we can, go ahead.
Maximum peak overshoot is given, sir.
Yeah, this is given. Correct. So,
Rise.
So, what we can do is, we are given the peak overshoot, right? That is 1.5266. So, can someone tell me the formula for peak overshoot?
Yes, sir. E के power minus pi zeta by under root 1 minus zeta square.
Okay. So, this implies e to the minus pi zeta by root 1 minus zeta square is equal to 0.5266. So, solve this equation for zeta. Tell me what you get for zeta. And anyone apart from Abhishek and Kiran, please?
Yes, sir. Calculate.
No, anyone apart from you two guys? You two guys are only answering.
0.165.
0.165.
Yes.
थोड़ा गलत लग रहा है. Can anyone else answer what they have got? I think the answer is theta equal to 0.2. Can someone verify this?
So zeta 0.2, sir. Got it.
0.2, no? Abhishek, maybe you have made some mistake. Just check it once.
Yes. Yes.
Yeah. So we now have zeta equal to 0.2. Okay, we have one parameter. We know any standard second order system can be written as this. Okay, omega n square by s square plus 2 zeta omega n s plus omega n square. And we have the given system is of this form: g by s square plus 3s plus g. So basically this g is omega n square. Correct. Now I have found out the desired zeta for getting this closed loop response. So the system must have zeta equal to 0.2. Now if we compare coefficients, we see that 2 zeta omega n is equal to 3. So from this we can obtain the value for omega n. So come on, tell me what should be the value for omega n?
$7.5.
7.5. Correct. So this is the value for omega n. So I want to find out the value for g, which is omega n square, which is 56.25. So yeah, we were given this system and we were told that we want the response to be this way. we were given information about the peak overshoot, and we were told to find out what the system should be, what the value of G should be. So what we did was we took the value for peak overshoot and found out peak overshoot depends only on the damping ratio. So we found out the damping ratio, turns out to be 0.2. Then we compared coefficients of the two, like the standard form of the second order system and what we have. So based on that, we obtained that omega n should be 7.5 and consequently G is nothing but omega n square. So we obtained this is G. Correct? Anyone have any?
Peak overshoot is difference between 1 and maximum thickness.
Sorry. So this is
1 plus the
point. इधर 1 plus लिखा था. Basically equate करना है e to the power this formula with whatever extra you have. Correct?
Yes.
So this is the formula for peak overshoot and this is the peak overshoot. Then we can continue forward. Anyone has any doubt in?
Yes, sir. May I ask one question?
Yeah, sure. Go ahead.
Sir, how do you get the value of zeta by taking logarithm on both sides?
Yeah. Basically, you'll solve this ln.5266 is equal to minus is equal to pi zeta by root 1 minus zeta square. Then when you take root 1 minus zeta square to the other side, you'll just square it and you'll get a quadratic in zeta, then you'll get this. Okay?
Okay, sir. Okay, sir.
Yeah.
स्क्रीन को जूम आउट करते हैं यस सर कीजिए सर
ओके
मतलब था कि सर वहाँ 1.5 to 6 है तो उसमें से -1 किए कि नहीं हुआ
हाँ वो मैं लिखा था कि this equal to 1 plus. So we'll move on to the next question. So for the previous system that we have and the desired for this system and for this desired closed loop response, find the value for Ts into Tp, where this is the settling time and this is the peak overshoot time. So what is the formula for both? Ts is, can someone help me?
4 by zeta omega n.
2% के लिए 4 by zeta omega n और 5% के लिए 3 by zeta omega.
Correct. So for this problem, we'll take the 2% thing. And what is the formula for peak time?
Pi
minus theta. Pi by omega.
Pi minus theta वो rise time के लिए.
Pi by omega yes.
Yeah.
Yes, exercise.
So come on, calculate these values. We obtained zeta as 0.2 and omega n as 7.5. So what should be the settling time and the peak time?
Settling time is 2.66 seconds, sir. Peak time is 0.427.
Correct. So we'll just multiply these two and what we get is 1.14. So are there any doubts in time response and things like whatever how we derive and things like that?
सर यहाँ पर मुझे कोई टाइम कांस्टेंट पूछता है सर सेकंड ऑर्डर सर्किट में तो वो कैसे कैलकुलेट करेंगे सर?
टाइम कांस्टेंट सेकंड ऑर्डर सर्किट के लिए
क्योंकि फर्स्ट ऑर्डर सर्किट के लिए तो 1/a होता है जहाँ पर a मतलब जी ऑफ एस
बट ऐसा कोई क्वेश्चन कहीं पे देखा है क्या?
मुझे एक मिला था सर ये एक था उसमें समझ में नहीं मतलब ऑनलाइन एक क्वेश्चन सर्च कर रहे थे तो उसमें मुझे कहीं दिखा था टाइम कांस्टेंट वो मुझे याद नहीं है किस समय मैंने सर्च किया था और मुझे मिल नहीं रहा, इसलिए
अच्छा,
सोचा आपसे पूछ।
I don't think there is any defined notion for time constant in a second order system, and basically to define a second order system only we have derived all these things like peak time and settling time, then peak overshoot and things like that, but I don't think there is any settling time thing, because in first order system we can say when the actual value has dipped to say e times or this kind of step response.
वन मोर क्वेश्चन सर, अगर जीटा का वैल्यू जीरो से कम हो या जीरो या वन के बीच में हो या वन से ग्रेटर है, वो सिस्टम स्टेबल है कि अनस्टेबल है कि मार्जिनल स्टेबल, वो कैसे जानेंगे?
डैम्पिंग रेशियो से स्टेबिलिटी तो पता नहीं चलता।
नहीं, ऐसा क्वेश्चन दिया हुआ है सर कि कोई सेकेंड ऑर्डर का कंट्रोल सिस्टम है और जीटा के वैल्यू लेस देन जीरो है, तो सिस्टम क्या होगा, स्टेबल होगा या अनस्टेबल?
लेस देन जीरो दिया हुआ है,
लेस देन जीरो सर। और उसके बाद पूछ रहा है कि सिस्टम क्या है, स्टेबल या अनस्टेबल।
अच्छा, तो द थिंग इज कि if I have a system s square omega n square minus some 2 zeta omega n s plus omega n square, ऐसा सिस्टम होगा ना अगर zeta less than 0 है, so let's say this is something positive।
थीटा क्या नेगेटिव हो सकता है?
फिजिकल कोई सिस्टम के लिए तो नहीं हो सकता।
ओमेगा एन एंड ओमेगा टी बोथ आर पॉजिटिव।
I don't
possible to make zeta less than 0?
I don't think for your usual no, like see, depends, like in the standard second order system the damping ratio basically denotes the damping term, like suppose you are looking at some oscillation, damping ratio basically बोलता है कि how fast or how the damping will happen, we have oscillations, when will it settle down or things like that. So if you have negative damping, then what it means is the system will so if I have a positive value of damping, then that means that if I have some oscillations, they'll die down, they'll damp away. And on the other hand, if I have negative damping, what that means is any oscillations that I have, they will keep growing, they will go unbounded. But in most of your physical second order systems, I don't think you'll have negative damping, because damping is usually things like resistance or like what do we have, friction and stuff like that. So damping term in any real world case for a simple linear second order system, I don't think it will be negative, but theoretically or maybe like by manipulating things, we can construct a second order system which will have an equation of this form. So when this happens, if I have a negative coefficient, so say I have s square plus 3s plus 2, tell me the roots of this equation. Is equal to 0. What should be s?
Minus 3
and minus 2, right? Yeah.
Yes.
So given, but if I had instead s square minus 3s plus 2 equal to 0, then what I will have is s is equal to 1 and 2. So what happens is, if I have a negative coefficient for a polynomial, then there will be at least one right half plane root. Okay, so then due to that the system goes unstable if zeta is less than 0. Is
yes,
that
unstable? Yes, unstable. One more question sir, कि कोई सिस्टम स्टेबल है तो उसके लिए मेरा जीटा के वैल्यू कहाँ से कहाँ तक राइज होना चाहिए? मतलब ऑप्शन में तो दिया हुआ है 0.4 से 0.7, 0.8 से 1 और 1 से 1.5, मतलब जीटा का क्या वैल्यू होना चाहिए कि वो सिस्टम मेरा स्टेबल रहेगा?
क्वेश्चन में और कुछ दिया है क्या?
नो सर, बस यही बोला है कि स्टेबिलिटी रहने के लिए कोई सिस्टम का उसके डैम्पिंग का रेशियो क्या होना चाहिए, मतलब किसके किसके बीच में राइज होना चाहिए। मैंने वो क्वेश्चन ग्रुप में भी भेजा है सर।
तो उसको प्लीज ये फोरम में पोस्ट कर देना, ग्रुप में बहुत सारे मैसेजेस आते हैं तो ट्रैक करना डिफिकल्ट रहता है। फोरम में डाल दो, लाइक वी आर अ टीम सो विल ट्राई टू answer as soon as possible. Okay, so you are asking
One more question, sir.
एक मिनट, just 1 minute. I'll think about that previous question. What the range of zeta should be? So राउत अरे पढ़ा है ना, तो राउत अरे यूज
Yes.
करके मे बी लाइक okay, just s is equal to minus zeta omega n plus minus root of 1 minus zeta square. This is the solution to the polynomial, right?
Yes, sir.
So basically for this, if this part is
Sir, it is asked in the response speed of a closed system, sir. I am
it is
from the
asked,
point of view of stability and response speed of a closed loop system, the appropriate range for the value of damping ratio lies between. This is the question, sir.
okay. Can you repeat the question just once?
From the point of view of stability and response speed of a closed loop system, the appropriate range for the value of damping ratio lies between.
अच्छा, okay.
ये तो क्लियर है सर कि रिस्पॉन्स स्पीड ऑफ क्लोज सिस्टम के जो बोल रहा है सर, इसके भी आपने, तो ये जो होगा ये अंडर डैम्प सिस्टम होगा सर, बिकॉज इट इज सेटल्ड फास्टली.
Faster, yeah, correct. So if you have an overdamped system, it will take more time, and if you have an undamped system, it won't.
Undamped system
won't settle.
at infinite time.
So zeta should
तो सर
be.
ये बता रहे थे सर कौन ज्यादा समय लेता है, कौन फास्ट होता है और कौन जल्दी स्टेबल होता है।
हाँ, मतलब अनडैम्प्ड सिस्टम में तो सिर्फ ऑसिलेशन से होंगे, करेक्ट? सो उसमें सेटलिंग होगा ही नहीं, सो इट विल नेवर सेटल. बट इफ यू हैव एन अंडरडैम्प्ड सिस्टम, then it will settle something like this. But if you have an overdamped system, it will be something like this, no?
Yes, sir.
Yeah. So here the settling time usually is there a formula for the settling time of this system?
Yes, sir. For 2% के लिए तो वही 4 by zeta omega n.
Oh, yeah, correct. 4 by zeta omega n. And
2% के लिए sir.
Okay. So okay, let's keep this frequency fixed omega n, and I'll vary zeta. Okay. So one case is I have zeta between 0 and 1. One is I have zeta greater than 1. That is for overdamped case. So if zeta is between 0 and 1, then 4 by zeta omega n is higher, no?
Yes, sir.
Okay, then by that, yeah, so basically for an overdamped system, the response time is faster actually. I made a mistake earlier.
Yes.
Yeah, this is clear, right? Because if zeta is lower, then settling time is higher. That is the relation. But the issue with overdamped system, what will happen is, so if I have an overdamped system, I will have poles of this form, correct? So here, this was J, but if it is overdamped, since zeta is greater than 1, I will have this, correct? So both of these will be real terms. So now if omega n root zeta square minus 1 is greater than zeta omega n, correct? So basically, okay, I'll write this in a, if the system is overdamped, then the system roots will be this. Okay, so I want to see if one of the root, that is one of the pole of the system, will be on the right half plane. When will that happen is if omega n root zeta square minus 1 is greater than zeta omega n, and this happens if zeta square minus 1 greater than zeta square. Okay, this will never happen, right? Yeah, okay. So what we have come to the conclusion that overdamped and underdamped both systems will be stable, because we have this, the real part is negative, and then response speed you can find out that using the settling time formula, you can see that as the damping ratio decreases, the settling time will increase. So is this clear, whatever we discussed now?
Sir, no sir. Overdamp और underdamp के लिए system कैसे stable है?
So see, okay, for overdamped system, you know that the roots are minus zeta omega n plus minus omega n, this thing, correct?
Yes.
तो मतलब कि एक रूट है माइनस जीटा ओमेगा एन प्लस ओमेगा एन रूट जीटा स्क्वायर माइनस 1, और एक रूट है माइनस जीटा ओमेगा एन माइनस ओमेगा एन रूट जीटा स्क्वायर माइनस 1. If damping ratio and this natural frequency both are positive, then this thing will be negative definitely, correct?
Yes sir.
And this thing can be positive if this part is greater than this part, correct?
Yes sir.
But that is never possible, right? Because this is omega n into root zeta square minus 1 minus zeta. So obviously zeta is greater than root zeta square minus 1. So we will always have poles in the left half plane, correct? If the system is overdamped. So, and if it is underdamped, then the poles will be minus zeta omega n plus minus j omega n root 1 minus zeta square, correct? So in this case also we have real part as this only. So we'll have a pair of conjugate poles on the left half plane. So in both these cases poles will be on the left half plane and the system will be stable. Is this clear?
Yes sir. मतलब कोई भी अंडर डैम्प हो और ये ओवर डैम्प हो तो उसका जो पोल होगा लेफ्ट इस प्लेन में लेफ्ट साइड में, इसमें तो वो स्टेबल हो गया.
स्टेबल हो गया.
और वही अगर क्रिटिकली रहता तो मेरा वो ओरिजिन पर रहता, मीन्स वो मार्जिनरी स्टेबल नहीं, रूट उसका इक्वल रहता अगर वो क्रिटिकली डैम्प रहता तो.
हाँ, बट ये टर्म जो है जीरो हो जाता, करेक्ट?
क्रिटिकली के लिए तो जीटा 1 होगा ना सर, तो उसके लिए मेरा जो रूट होगा सेम रूट वाइज होगा. मतलब वो भी तो दोनों लेफ्ट साइड में था, वो भी स्टेबल ही होगा.
वो भी स्टेबल ही होगा, करेक्ट. जीटा क्रिटिकली के लिए जीटा 1, हाँ, तो स्टेबल है, करेक्ट.
और लेकिन वही अनडैम्प रहेगा तो फिर वो मेरा इमेजिनरी पर रहेगा, मीन्स वो मार्जिनरी रहेगा.
नहीं, अनडैम्प्ड होगा तो माइनस समथिंग प्लस माइनस जे भी होगा ना, तो इमेजिनरी एक्सिस
अनडैम्प्ड के लिए तो जीटा 0 होगा ना सर, तो इमेजिनरी होगा.
हाँ, तो ये 0 है तो ये प्लस माइनस जे समथिंग भी कुछ भी, हाँ, तो वो इमेजिनरी एक्सिस, तो वो मार्जिनरी स्टेबल. हाँ सर.
और जो ओवर डैम्प होगा तो वो भी स्टेबल ही होगा क्योंकि
वो
उसका
भी स्टेबल होगा, वो दोनों रूट्स लेफ्ट साइड में होंगे.
इस क्वेश्चन के अनुसार कौन सा ऑप्शन होना चाहिए सर? इसमें तो अंडर डैम का दिया हुआ है सर.
So,
हाँ,
I am reading the options, sir. Option A 0.
Let me just write. हाँ, क्या है? Option A
0 to 0.2.
Okay, 0 to 0.2.
And option B 0.4 to 0.7.
Okay.
And option C 0.8 to 1.0. And option D 1.1 to 1.5.
Okay, so I guess we can say that this can be the answer, right? Because if you have 0 to 0.2 अच्छा ये पहले बोलो कि ब्रैकेट ओपन है या क्लोज्ड है, लाइक 0 इज इंक्लूडेड इन द इंटरवल और नॉट इंक्लूडेड.
Sir, this is not in the form of bracket, sir. This is simply 0
to
to
0.2.
0.2. It means 0 is included.
Okay, if 0 is included then that will be marginally stable, right, which you do not want to have ideally. So you want to have a properly stable system, and
These are the approximate values of zeta.
which are
These are the values of zeta.
these are the values of zeta. So if zeta is 0 then you have a marginally stable system, right?
Yes, sir.
So if I have a marginally stable system, I usually do not want to have it near there. So maybe I can go with this option, so that I have a range because we saw if zeta is less. No, wait a minute. What did we see? We saw that zeta is lower than settling takes more time. Okay, sorry. So if zeta is lower, then settling time is higher. So I want to have as high zeta as possible, so that settling time will be as low as possible. And 0 is the marginally stable thing. So if I go to increase zeta, then I'll have lower settling time and I'll be far away from marginally stable situation. So I'll be comfortably in the stable zone. So I guess we can go with option D and take an overdamped system.
ऑप्शन डी इज द करेक्ट आंसर, लेकिन थोड़ा एक्सप्लेनेशन समझ में नहीं आ रहा सही कैसे. क्योंकि ऑप्शन सी और डी पर भी तो देखने के बाद वो दोनों भी तो मेरा सिस्टम स्टेबिलिटी में ही आएगा, क्योंकि एक है क्रिटिकली डैम्प लेके चल रहा है, वन डैम्प है.
ये तीनों में सिस्टम स्टेबल ही आएगा, बट सेटलिंग टाइम विल डिक्रीज विथ जीटा ना.
तो जितना सेटलिंग टाइम कम रहेगा उतना ही सेटल होने में ज्यादा समय लगेगा, ये मीनिंग हुआ. तो कोई भी
नहीं एक
मतलब कोई
सेटलिंग टाइम जितना कम हुआ, सपोज सेटलिंग टाइम 1 सेकेंड है और एक केस में सेटलिंग टाइम 10 सेकेंड है, देन 1 सेकेंड वाले केस में बाय 1 सेकेंड वो सेटल करेगा ना, और 10 सेकेंड वाले केस में बाय 10 सेकेंड से सेटल करेगा.
यस सर. फास्ट कौन सा जल्दी सेटल किया सर? तो जल्दी सेटल करने और तो 1 सेकेंड.
हाँ तो वही ना, तो आई वांट लोअर सेटलिंग टाइम्स. तो एंड सेटलिंग टाइम हम देखे कि इज इक्वल टू क्या, 4 जीटा ओमेगा एन है. तो जीटा बढ़ेगा तो सेटलिंग टाइम घटेगा, तो जितना हाई जीटा होगा उतना कम सेटलिंग टाइम होगा, और ये सिस्टम स्टेबल भी है, तो ऑप्शन डी ही ठीक होगा.
नहीं तो ऑप्शन डी नहीं, बी दिया हुआ है.
अच्छा बी दिया हुआ है.
यस.
रेस्पॉन्स स्पीड बोला है ना.
यस.
ओके, तो और क्या मीनिंग हो सकता है इसका? तो ये राइस टाइम का फॉर्मूला क्या होता है? पाई माइनस थीटा बाय ओमेगा एन रूट 1 माइनस जीटा स्क्वायर ना.
यस सर.
तो मे बी बाय रेस्पॉन्स स्पीड वी शुड, तो इसमें क्या होगा, जीटा बढ़ेगा.
गूगल पे ये बता रहा है ना सर कि अगर हम जीटा के वैल्यू 1 से ज्यादा लेके चलते हैं, मतलब 1 लेके चलते हैं, तो मेरा पीक ओवरशूट ना 1/√1 माइनस, मतलब वो चला जाएगा 0 चला जाएगा पीक ओवरशूट. वैसे देख
मतलब वो ओवरशूट नहीं होता, काइंड ऑफ
1 हो रहा है ना सर. 1 से ज्यादा लेके चलते हैं तो वैसे ही कैलकुलेट करके बता रहा है सर गूगल पर भी, क्योंकि
मैं जो सोच रहा हूँ, व्हाट आई एम थिंकिंग इज, सिंस लेट्स से पीक टाइम अगर लेते हैं जो कि पाई बाय ओमेगा एन रूट 1 माइनस जीटा स्क्वायर हुआ, तो इसमें जीटा बढ़ा तो रूट 1 माइनस जीटा स्क्वायर घटेगा, तो टीपी बढ़ेगा ना?
ऐसे ही
नहीं,
ऐसे नहीं लेके चल रहा सर। जब जीटा का वैल्यू 1 से बाहर होगा तो मीन्स इमेजिनरी पार्ट आ जाएगा, अंदर 1 माइनस जीटा।
हाँ हाँ, अच्छा हाँ, सॉरी एक मिनट। तो अगर सॉरी हाँ, तो अगर जीटा घटेगा तो रूट 1 माइनस जीटा स्क्वायर बढ़ेगा, तो टीपी घटेगा, राइट?
यस सर।
तो मे बी वो लॉजिक लिया जा रहा होगा इस क्वेश्चन के लिए, लाइक रेस्पॉन्स स्पीड मीन्स कि कितना जल्दी कुछ एक रेस्पॉन्स दिखता है सिस्टम में। तो अगर उस लॉजिक से चले तो लोअर द जीटा फास्टर द रेस्पॉन्स विल बी, बट हम 0 भी लेना नहीं चाहते क्योंकि वो मार्जिनली स्टेबल हो जाएगा, तो ये 0.4 to 0.7 वाला रेंज लेंगे। So with that we can wrap it up for today. We'll meet same time next week. So thank you for attending this class.